Okay, hi there Year 8 students. We're just going to spend a few minutes going over some of the answers to the revision that was given out in class today. So hopefully you've checked your answers and are ready to resolve any problems that you may have had. Okay, so we'll kick off with the first page. So we'll start off with complementary events. So remember that two complementary events together will make up the whole sample space for a particular situation. So say rolling a die, for example, if you were to say roll a 2, for example, the rest of the sample space, the complement of that event is to roll a 1, a 3, a 4, a 5, or a 6. It's every other outcome that's possible. So for each of these on here, we had what's the complementary event for each of the following. So from a bag of numbered marbles selecting an even number, well, you think, well, what's every other possible outcome in that situation, which is where selecting an odd number comes from. For the alphabet, if you imagine every letter in the alphabet and the event that we're looking at is selecting a vowel, the complement of that is every other letter in the alphabet, which are all the consonants. The rest are on a similar sort of theme, so heads complement of that is tails. The only tricky ones that I think I'll point out for this one are rolling a die and getting a number less than 3. So for this one, the thing that can trip you up is if you think about the possible answers for rolling a 6-sided die, when it says getting a number less than 3, that's really just referring to 1 and 2, because they're the numbers that are less than 3. So the complement of that is going to be the numbers that are greater than 3, as well as 3 itself. So 3 or greater is what we're looking for that one. The other tricky one from memory was, I don't know, the rest of them were all pretty good. The last one though was, well, what's the complement of selecting a blue marble from a bag of marbles? The complement of that is selecting a non-blue marble. We don't know what color the other ones are because the question doesn't tell us, but we know that the complement of choosing a blue marble is a non-blue one. It's anything that's not blue. So that's okay to have as your answer for that one. And the rest are all on the same sort of lines. But if you've got any questions about the ones that were there, then, definitely, give me an email or ask me in class. Okay, for the next one, so for each of the following, state whether the pairs of events are complementary or not. Okay, so each of these will give you a situation, and it's essentially asking you if the two, outcomes it's given you represent all of the possible outcomes for that particular situation. So looking at the first one, for example, so if the event is having Wheat Bix or cornflakes for breakfast, the question is, are those two complementary events? The reason that the answer is no is because eating Wheat Bix or eating cornflakes together don't represent every possible outcome for what you could have for breakfast. You could have some yogurt or some hash browns or some eggs or nothing, but Wheat Bix and cornflakes are definitely not the only two, so they're not complementary. Similar story for the second one. So walking or riding your bike to your friend's house, they're not complementary either. You could run there, you could get driven, you could be like Mr. Bissett and ride your electric skateboard there. They're certainly not the only two ways you can do it. Same for watching TV at night and listening to the radio. They're not the only two things that you can do. The only one that sticks out there is that for passing your maths test, because failing or passing are the only two possible outcomes, those two are complementary events. So things like passing and failing a driving test, you'll see that come up as a common example of a way to ask this question. And for the last one, rolling a number less than 4 or rolling a total greater than 4 on a 6-sided die, that one does trip you up a bit. They're actually not complementary. The reason is, if your possible outcomes are 1, 2, 3, 4, 5, and 6, your numbers less than 4 are 1, 2, and 3. Numbers greater than 4 are 5 and 6. But because they didn't include 4 in either of those, they've not represented every possible outcome, so therefore they're not complementary events. Even though it looks like they would be, they've just sort of tried to trick you with that one. Okay. Next one, the only statement that doesn't involve complementary events is A. So it's similar to the other question where there's many ways to travel to school and bus and car are not the only two. So that's A for that one. I'm getting used to my new stylus, by the way, so I'm hoping that's coming across nice and clearly. The next one was about athletes competing in a race. Now, what you're looking for here is that complementary events, their probabilities, because they represent every situation or every outcome in the sample space, their probabilities will always add up to give you 1. So the reason that we know that the probability, well, if we're given the probability that the athlete in lane 1 winning is 1 out of 5, we know that the probability of someone else winning is 4 out of 5. Because those two events together, like someone's got to win out of all of them. So if it's not the person in lane 1, it's going to be one of the other athletes. So that's why the probability of that is 4 out of 5, because that's what we'd need to add to 1/5 to make it equal to 1 whole. Okay, we'll start flicking through now. The sample space questions, this first one was pretty, this one here was pretty straightforward. Remember, listing the sample space is listing all the possible outcomes. So sample space of rolling a 6-sided die is going to be 1 through to 6, like so. I won't spend too much time on this one because this one was pretty straightforward. So probability of rolling a 6, for example, there's only one possible outcome in those 6 events where only one of them is 6, so that's 1 over 6. Even number, there's 3 even numbers out of 6, which you then simplify to 1 over 2. The only tricky ones, we've got, say, a number greater than 4. Just be mindful that that doesn't include 4, so that's only 5 and 6 for that one, which is why you get a final probability of 1 over 3 for this one. The last two, the probability of getting a 7 is 0 because there's no way that you can get a 7. And for the last part of it, so the numbers that were factors of 60, just here, so for that one, all of those numbers will fit into 60. Like 6 will fit in there, 5 will fit in there. A few of you didn't think that 4 went in, but remember 4 will go into 20 and 20 goes into 60. So that's a way that you could figure that out quickly. All of those will go into 60. So the probability that a number chosen is a factor of 60, well, it's certain. It's 6 over 6, which is 1, which is certain. Cool, moving on to and or. So the first question looked at or. For this one, you had to do a little bit of work yourself and find that the total number of vehicles in the car park was 180 by adding 8, 160 and 12 together. It's really hard to write with this. It's more easy writing on the screen. Maybe I'll just write on the screen next time. Anyway, so for this one, the first one is pretty easy because we just look at the number of buses, which is 8, so 8 out of 180. Car is easy because there's 160 cars, so the probability of choosing one at random is going to be 160 over 180, and then you simplify from there. Where it gets a little trickier is where you have to find the probability that it's either a bus or a motorbike, because for that one, you've got to take those 8 buses, add them to the 12 motorbikes that are there, which is where the 20 here comes from. So it's 20 vehicles. It can be a motorbike or a bus, so either of those are fine. That's why we add them together out of the 280, which gives us 1 over 9. And similar story for the answer being not a car. For this one, we're looking for every vehicle in that sample space that isn't a car, which is just the 20 cars and motorcycles that we did in the last part of the question. So that's actually the same for that one. Okay, moving on to the Venn diagram. That shows the number of people who have a university degree and the number who are now employed. So the total number of people surveyed, you add each element in there together. So you've got 3 plus 10 plus 5 plus 2, which gives you 20. Next one, the total number in the survey who are employed. We're looking there at all of these people here. It's every person that belongs in the employed set just there. So there's 15 people in there. So you'll remember for that one, there's 10 that also happen to have been to university, but they belong to both sets, so that's all fine. The next one, proportion of people in the survey who are employed. So it's those 15 people out of the 20, so 3 and 4. The number of people who have a university degree and are also employed, because we've got and for that one, we're looking for the people that belong to both sets, so that's those 10 people in the middle. So 10 out of 20, which then simplifies to 1 over 2. So remember that word and means that they've got to belong to both of them. If the question had said how many people went to university or are employed, We could add all of the people together in both sets like this. We could have the 3 people that just went to uni, the 10 who went to uni who are employed, and the 5 who are employed but didn't go to uni. If we were doing or, we'd use all 3, but because we're looking at and for this question, we're only interested in the intersection for that one. Okay, moving on again. So using a two-way table to show a sample space for the following event. So we've got tossing a coin, which we've represented here on the left-hand side, and spinning a spinner, which we've put along the top there. So in a test, you'd need both sets of, or both components to the experiment. So if you've got a coin or a die or a spinner or whatever it is, you've got to have a row or set of rows or set of columns representing those. You've also got to represent every possible outcome. You've got to represent the sample space as well. So say for coins and a spinner, for numbers like this, oh, that box is dreadful, I apologize. For something like that, you've got heads and a 1, heads and a 2, so labeling that clearly is pretty important. So another tick for your sample space there as well. The other probabilities in there are pretty straightforward. There's a little bit of and thrown in there as well. So for the first question, heads and a 1, there's only one way you can roll, spin and get a 1 and toss a coin and get a heads. So there's only one way that both of those happen. Further down, tails and an odd number, there's 2 ways that you can do that. So tails and 1 and 2 and 3. So even though it's still an and question, there's only a couple of ways that you can, there's still a couple of ways that you can do it, even though it's got to satisfy both of those things. The only other one that was a bit tricky was tails and a prime number. Remember, prime numbers can only be divided by themselves and 1. So tails and a prime number, that would be getting T2 and T3, which is where that answer of 2 out of 6 or 1 in 3 comes from. The copying and completing the two-way tables, that's a little harder to show you because that's already filled out. But essentially for each of the numbers that have been filled in black just here, for these two-way tables here where you've got literally 2 rows and 2 columns and it's showing people that are in or things that belong to a particular category or not, for these ones they'll also show the totals for each row and column as well as the grand total in the bottom corner. So the way that you work through these ones is just to essentially chip away all the little bits of information until you've filled out the whole thing. So say there's 50 here, for example, we'd say, well, there's 20 people that belong to A and B, there's 70 people that belong to A in total, which means the missing number is the 50 that I've already placed in there. So I know that I need to add 50 to 20 to give me that 70. Then you start filling it from there. So 70 plus something gives you 100, that something has to be 30. 50 plus something gives you 60, the something has to be 10. 20 plus something gives you, oh hang on, I've gone the wrong way around. 100 is given by 60 plus something, so the something has to be 40. And then up here, 20 plus something gives you 40, so the something has to be 20. So for that one, you're making sure you're basically filling out the little bits of information that you can, and eventually you'll have every missing piece of information. What you can do then is check each row and each column to make sure that they add up to what's at the end in the total section, and also make sure your grand totals add up to give you the right amount at the end as well. So that works. For the last one here, we had 5 and 3, they add to give you 8. You then say 10 add 8 gives you 18. You then know that something plus 7 gives you 18, so the something has to be 11. 5 plus something gives you 11, so the something has to be 6. And then 6 plus something gives you 10, which is where that 4 comes from. So for these ones, you just look at what you can fill out and just gradually start chipping away. But as long as each row and each column adds up to what you expect it to, then you're halfway there for that one. Excuse me. Okay, so now knowing the relationship between the two-way tables and the Venn diagram is really important. So for table A, let me see if I can choose a different color for this. I'm sure I have the ability to do that. So when we transfer this to the Venn diagram, these 20 people that belong to both group A and group B, they go in the middle because they belong to both sets. They're in the overlap between the two sets. These people here, these 50, belong to A, but not B. So therefore, those guys have got to go here in that section. On the right of that, so the people that belong to B but not A. It's getting so messy, I apologize, but I think it's just the nature of writing on the screen. Then we've got the 10 people that belong to neither who go on the outside like that. Then it's a similar situation to for the second two-way table. So 6 people belong to both. We've got 5 people that belong to A but not B. We've got 4 that belong to B but not A, and then 3 that belong to neither. So transferring between the two, that's what you're looking for there. And I think we're on the last page. That's exciting. Congratulations if you've managed to stick with me until this point. So in year 8 of the school, there are 40 boys, half of whom are in the racing club. Of the 100 students in year 8, 35 are in the racing club. Oh, okay, so this is an example of a hard question. This is more of an extension sort of thing. So I'll show you how you would figure that out. Okay, first bit of information is to say, well, there's 40 boys in total and half of them are in the racing club. So when you get your Venn diagram underneath just here, you know that there's 40 people in total, 40 boys. Half of them are also in racing, so that's where the half in the middle comes from. The other half are boys that are not part of the racing club. We know that there's 35 students in total in the racing club. So everyone in the racing club there, every element in that set's got to add up to 35. So that means that 20 plus something will give us 35. So that something has to be 15. And we're also told that there's 100 students in year 8. It's a pretty small year group, but anyway. So we've got 20 who are boys that don't do racing, 20 who are boys that do racing, 15 people that aren't boys that do racing, which means that there's 45 people left who are neither boys, so girls, who are not in the racing club. So that's where that Venn diagram comes from. Now, probability is a percentage that a randomly selected student is a boy in the racing club. So that's the 20 in the middle. So 20 out of 100, which gives us 20% for that one. A girl in the racing club, that's these 15 persons just here. So it's 15 out of 100, which is 15%, is not a boy. So that's everyone that's outside the boy set on there. So 15 plus 45, which is 60. It's kind of antiquated to go girls and boys, but hopefully it's, they're the sort of examples we might start seeing less and less, I think. And finally, students that are not in the racing club, we're looking for everyone that's outside the racing set. So the 20 people who are boys that are not in the racing club, as well as the 45 that are girls not in the racing club. So 65 in total for that one. And just as a point of interest for some of you, I guess, the last 2 questions are actually at that level. They're not going to be on the test because they're using what we call conditional probability. So don't feel that you need to learn this because you'll do this next year and you won't be assessed on it this year. But it's saying what proportion of the year 8 racers are boys. So what it's saying there is it's narrowing down the sample space to just the year 8 racers, and it's asking of them how many are boys. So that's what we call conditional probability. It's saying, well, based on the fact that they're in year 8, they're a year 8 racer, what's the probability that they're a boy? Same for if they're a girl as well. So that's just a little bit outside the realm of what we need to know. But if you did want to still have a go at them, I've got the solutions on the page as well, and you can ask me in class too. Okay, now we go back to Jake Peralta. We say, great news, Jake, we've finished our revision. He's happy, we're happy as well. Any questions about any of this stuff, make sure you bring it to class and I'll see you there.